Thank you very much. It's a pleasure to be here and a distinct honor to receive the Exner medal. I would like to share with you some of our work, actually discovered originally in the mid-1990s, on how to make ultra-porous crystals. And then since then, we've been developing their chemistry and also their applications, their many applications, especially in what I call for a sustainable future, as you will see, in clean energy, clean water, and clean air. Let me just back up just in one slide, express that for the last, I would say, almost 100 years, chemists have honed in the skill of stitching atoms together to make molecules. And of course, things like pharmaceuticals have benefited from this skill, and so did society at large. The chemistry that we developed is about taking those molecules and stitching them together, taking molecules in general and stitching them together to make extended structures or materials. And thus the emergence of what I call reticular chemistry. Reticular chemistry I define as linking of molecular building blocks by strong bonds to make crystalline extended structures. There are three main components of this definition that are absolutely essential and new to chemistry. One is building extended structures from the molecular building block approach so that we can begin to think about designing structures rather than making materials by what we used to call the shake and bake approach. And the second thing is once you make these materials, you find that they are linked by strong bonds and therefore they are robust. So if you're making a CO2 capture material, it can stay in a power plant for many, many years, operating without having to regenerate the material or reassemble the material. Same thing for what I will call water harvesting from air. You want these materials to be robust so that they can operate many, many cycles for many, many years. Third, we want them to be crystalline. Every chemist wants their material to be crystalline because X-ray diffraction and electron diffraction are the most important techniques to figure out the underlying atomic arrangement of those structures. And so these are the three important things that we have developed in reticular chemistry for making extended structures, what chemists call infinite structures, or materials. And a product of reticular chemistry one of the products has been metal organic frameworks, or MOFs. This is a typical MOF. It's made from the blue tetrahedra are the metal oxide units. This is a multi-metallic unit. It has 4 zinc centers, 4 zinc tetrahedra, and then they are linked by organic, as you see here, into an extended structure. This is a fragment of the structure. And the yellow ball indicates the space within which one can bind other molecules like carbon dioxide or water or other molecules, even when you make larger pores, even proteins and other biological molecules could be used. The special thing about this chemistry is that everything you're looking at is variable, is that you can actually vary. And this is what chemists like. Chemists love control. You can actually control everything in this structure. You can control the size, the length, the functionality, and connectivity of the organic unit. You can control how many metals represent this multi-metallic unit. So you control its size, you control the type of metal that it has, and you control also its connectivity. And thereby, you're controlling also the pore size, the pore geometry. And when you start thinking about modifying the metal centers and modifying the organic units, now you can fashion the pores so that you have a functionalized pores, ideal for binding an incoming substrate. So what we've done here is that we've opened the door to an infinite, what I call infinite open frontier. And when you think about it, there are billions and billions of possible structures. If you just think about tetrahedral structures alone, there are 10 or more million, 10 million structures that are possible. So think about all the different geometries of molecules that could be assembled into extended structures. So the infinite, you can think of it as an infinite number of structures, and already we and others are pursuing hundreds of applications ranging from what I've already mentioned, plus others in biotechnology and medicine. They're atomically precise, and they're ultra-porous, as you'll see shortly. The MOFs are now, for the last 10 years, they're architecturally stable, thermally stable, and chemically stable. Okay? So please don't ask me if MOFs are stable, because that is a question depending on your application. So you want them to be robust like rocks if you're trying to trap CO2 from air so that you can keep them in a device for many years. You don't want them to be very stable when you're using them, let's say, for slow release of drugs. Okay? So you want them to disintegrate. So, and then they can be scaled up to multi-ton quantities, as I will show shortly. The second class of materials that resulted from reticular chemistry is what we call covalent organic frameworks, and due to time consideration, I want to make sure that I at least show you one of these structures. And you look at the backbone of this structure. This is a structure that we can crystallize. And many years ago, I and many others thought you cannot crystallize structures of this kind. These are extended, in this particular case, 2D structure, made entirely from carbon-carbon bonds and carbon-nitrogen double bonds. And therefore, the backbone is extremely robust. Okay, this changes organic chemistry from molecular chemistry into extended structures. And you can see the powder diffraction shows that the structure, the COF, is stable, even in concentrated acid, base, and corrosive media. And that's the kind of stability you want if you want a material that's going to be in a power plant capturing CO2 or in the desert capturing water from air. So that's so what I'm trying to say is that we have laid the foundations over the last 30 years or so for this chemistry, which is now at the forefront of solving the climate issue problems. There's another class of materials we invented in 2016, and that is molecular weaving. It turns out there are families of molecular woven structure that could be made. We made some of them and reported them for the first time. And they're basically threads, molecular threads that are interlaced in and out of each other to make materials that are not just porous and robust, but also they're flexible. So they have many applications in making materials that are hard, but also tough, meaning they are not brittle. So this will be transformational for advanced material. I won't be able to talk about these, unfortunately, today due to time limitation and the focus on sustainability. So what is it on a fundamental level that these structures have done, the porosity of these structures? We've taken a particle like, let's say, a pebble or a piece of sand, and which would have, the surface would have a small surface area, 1 meter square per gram, and we expose every atom in that structure. So we opened up the structure. When you open up the structure, you get a surface area of 7,000 meters square per gram. Okay, you make an ultra-porous structure. Why? Because now when you open up the structure using the building block chemistry I just described, you make every atom in that structure an adsorptive site. This is another MOF made from metal oxide units here in pink and organics. And we know from crystallography of gases in the pore that everything you're looking at, whether it's the metal oxide units, the edges of the 6-membered rings, or the faces of the 6-membered rings, are actually binding sites for molecules like hydrogen, water, CO2, and other gases. That's what makes them so porous. This particular structure has a surface area of 6,400 meters square per gram. Okay, and that's equivalent for 1 gram of material, which is about a few sugar cubes. on the atomic level, they would cover an entire football field. And that's the space onto which one can compact gases and store them. Here's a movie that illustrates the point. Gases like to fill very large volume, and the difficulty is how do I compact them into small space, and how do I design a material that would pluck out CO2 from air or from flue gas. And here in this, let's see if this movie works. But I think an important contribution here is that these materials are crystalline, so they are characterizable fully on the atomic level. And you see when you talk about crystalline materials, that means the structure on the molecular level is exactly the same everywhere. The pores are homogeneously distributed throughout the material. And the idea is, could we take these porous structures and compact gases in the pores? For example, in the case of hydrogen, compacting hydrogen in the pores and making, let's say, a hydrogen fuel tank or a natural gas fuel tank. Both of those we have been working on. And in the case of CO2, as you will see, functionalizing the pores so that we can pluck out CO2 from air. And in some structures, being able to also trap water from arid environment. So they can be scaled up to multi-ton quantities. We have teamed up with BASF for many years, and this is a plant that is producing MOFs. This is if the MOF is made from a zinc, it's white, it looks like this. If it's made from other metals, it depends on the metal color, and also the MOFs can be shaped into different forms to allow you to use it in various applications. So this chemistry is about a chemist imagining a structure, making the structure, and building a device that ultimately will reach society. That's what I'm going to show you in the two cases that I will discuss shortly. This has never been the case, by the way, in chemistry, that a chemist can do all of this in a short period of time and in the same laboratory. So these are the molecules that we've been working on, and I want to focus today on clean air and clean water. In the case of CO2 capture, the problem is that you need to capture CO2 from air where it's almost double what it used to be since before the Industrial Revolution. It's dilute, but it's still significant concentration that we need to take it out. Even if we stop burning fuel today, we need to clean the air from CO2. The point sources like power plants, depending on what that power plant is burning, if it's natural gas, you have about 5% of the flue gas is CO2. If it's burning petroleum or coal, the flue gas has 16% CO2. This is an easier problem to address, as you'll see shortly, than this one, because this is, although double what it used to be, it's still dilute system, and you're trying to capture CO2 from a dilute environment. So to make a material that is ideal for carbon capture, you need a material that has high capacity, water stability, oxidation stability, cyclability. Regeneration temperature has to be low enough that you're not putting in a lot of energy into the system to recycle the CO2. So, and scalability, you want to be able to scale in this chemistry. So we've been working on carbon capture way before carbon capture became fashionable. Back in the 90s and since the 90s, we have shown that we can make different kind of materials. And I just want to summarize and say that in a MOF-filled cylinder like this, like you would have in your laboratory, we can store 18 times the amount of CO2, even though the MOF occupies volume in the tank or in the cylinder. So that means that the MOF acts to compact or bring CO2 molecules into the pores and compact them within smaller space. And so that tells you what the capacity could look like eventually. Here's a MOF that is programmed by virtue of having functionalities like, in this case, glycine. Glycine has a carboxylate on one end that binds to the metal on the multimetallic unit, and on the other end it has an NH2 unit. okay, a primary amine, chemist language. And that primary amine is ideal for capturing CO2 from air. CO2 goes to that amine unit, binds to that amine unit to make carbamate or carbamic acid, depending on how much water is being bound to the cavity. So this is something we've been working on, and that MOF we call MOF 808. We scaled up to a kilogram quantity, and we built a prototype in my lab to show that, in fact, this MOF can trap water, in this case, CO2 from air. Here's a CO2 at 400 ppm with some humidity, typical of what would be, so this is basically air. And we pass the air through the MOF, and you can see that the amount of CO2 produced at the end is less than 0.02 millibar because of the binding of CO2 to the pores from air. So it works, okay? And in fact, you can repeat this process 80 times, okay? You can take in the CO2 and remove the CO2, take more CO2, remove that, and so on. Here's a flue gas. When it's 15% CO2, this is conditions of flue gas, and you can reduce the flue gas from 15% CO2 to less than 2% CO2. So we think that this is a very important illustration that MOFs work for carbon capture. Okay, there are many things that we have to do. We have to scale it up to more than a kilogram quantity, which shouldn't be hard. We were scaling MOFs with BASF to multi-ton quantities. And we have to show that, in fact, this can do many cycles, up to 100,000 cycles. Okay, that's basically what the requirement would be. We have also been working on COFs with very strong backbone, such as these, and functionalizing those COFs with amine units. And these amine units take up from air 0.3 millimole of carbon dioxide per gram of material. And for flue gas from natural gas, 1.9 millimole CO2 per gram, and from coal, 2 millimole of CO2 per gram. Okay, so it's great for this, and for DAC, it's already taking up 0.3 millimole CO2 per gram. That's significant. And our target is to get close to 1 millimole from air. If you can have a material that takes up 1 millimole of CO2 per gram, and it can cycle 100,000 cycles, then you can commercialize this material, okay? And this material would stay in the device for many, many years because the backbone is made entirely from carbon-carbon bonds and therefore extremely stable backbone. So I would say there is hope, okay? We have achieved materials that perform very well, and in fact, there's already a material that is being deployed in industry, a MOF material for capturing CO2 from cement plants. This is a work that is coming out of the University of Calgary. So that's what I want to say about CO2. Concerning water from air, I don't think Austria has a problem with water, but the rest of the world, a lot of countries around the Mediterranean have a problem with water, as well as the US, Western US. A lot of these red regions are water-stressed, water-stressed regions. And our idea is that if you could make a MOF that takes up water from arid air in these regions, then you should be able to take up water from humid air where there may be plenty of water, but it's not clean. Okay, so could we, my vision has been, could we harvest water from air anywhere in the world at any time of the year? These red regions here, they've got plenty of water, but it's frozen. That's why it's in red. Okay, but so the idea is that we want to make something that works in the arid region where the humidity is typically 30%, 40% or less. Okay, even down to 10% sometimes. So before you tell me that these materials are going to dry the air, there's plenty of water in the air, okay? There's almost 13,000 cubic kilometers of water in the air at any one time. There's as much water in the air as we have in lakes and rivers on our planet. So if I serve each person in the world 50 liters a day, I would have only used less than 0.001% of the water in the air. Okay, so there's plenty of water in the air, and I think if we can trap some of that water to generate drinking water, then we would have used a natural resource that is recyclable. Now, nature has done this for high humidity, not for low humidity, but for high humidity. This beetle lives on the coast of Namibia, and as fog comes in from the ocean, water particles sits on the top, on the back of this beetle, where there are nano ridges onto which water nucleates, and then the water droplets grow. And by virtue of these nano regions being hydrophilic and hydrophobic, water in the end seeps down. Okay, hydrophobic regions propelling the water droplets to seep down so that the beetle can be hydrated. But at low humidity, there is nothing out there, even though you might buy something from Amazon that claims to take up water from low humidity. It doesn't, because it works on the cooling cycle. So let me show you why it's difficult to harvest water from air. Okay, here's a psychrometric chart. I have colored the arid regions in brown and the humidified regions in green. And you see here the relative humidity lines. So if I'm in a Mediterranean environment like Crete, let's say, I could have near the summertime, 30 degrees Celsius temperature, 20% relative humidity. For me to get water out of that air, I have to cool down the air to 4 degrees Celsius, okay? And that's not a viable solution, because that's a lot of energy that you have to put in. However, if you have a MOF that takes in the water, then you concentrate the MOF in the pores the water in the pores of the MOF. I put that MOF in a box, close that box, and expose it to the sunlight. Now the water humidifies the box. So I've turned desert air into tropical air. Okay, now my humidity is about 90% relative humidity. Okay, and to get that water out, make it drinking water or make it liquid water at 100% relative humidity, I have to only cool down by a few degrees Celsius. And that's the key to how the MOF will operate. And like everything else, whenever you make a discovery like this, everybody says, well, we've been doing this for a long time and it works and blah, blah, blah. And then when you look deeply, it doesn't work. So zeolites, polymers, I won't go into this, but none of these materials really work, because they need either a lot of energy to take the water out, like zeolites, we all know that they take up water from air, but you need to heat them up to 200, 300 degrees Celsius to remove the water. These definitely don't take up water from air in arid regions or in low humidity. And salts work very well at low humidity, but you need a lot of energy to take them out, and their capacity, kinetics is not very good. So this is a first MOF where we discovered this, and the students came in with this kind of isotherm where the water uptake in the material is shown in red. And immediately I looked at this and I thought, oh my God, this material takes up water at 20%, at around 20% relative humidity. Okay, that's low, that's very low humidity. That's typically what the humidity is in most deserts most of the year, or desert regions, I should say. And I think the other amazing thing about this material is that it takes up the water in I would say, a cooperative fashion. There's a very sharp uptake behavior, which tells me there's some cooperativity in the way the water is going into the pores. And the third, I think, amazing thing is that you can take out the water in green here at 45 degrees C. So as someone who grew up in the desert, I realized this material could harvest water and deliver water in the desert, because at night I could expose the MOF to air and water would go into the MOF, and during the day I can put that MOF in a box and harvest water by ambient sunlight shining onto the box. Of course, the student didn't believe it. but they will later. Okay, so then what we did is we cycled to show that in fact water can go in and out. And you can see here about 80 cycles. I think we did here 80 cycles. And we noticed that after the first cycle, there's a slight drop in capacity, and then there's stabilization. And so we wanted to look into why we have this drop. And the nice thing about having worked very hard on the crystallinity of these materials, that now we can go in with X-ray crystallography and neutron diffraction and examine where the first water molecules are residing. And we find that they are in the pores and they're interacting with the metal oxide units. And as you increase the amount of water in there, they can make tetrahedral shapes or cubic shapes. And it turns out these are the seeds that are bound tightly to the metal oxide unit, onto which other water molecules from the air will be bound. Okay? So this is why you have a cooperative phenomena, is that these seeds invite other water molecules to bind and help in the filling up of the pores. And indeed, we never take these seeds out. They stay in the MOF. So when we take out the water, we only take out the water that comes after these seeds came into the pore. And so the student didn't believe that this could work. So I asked them to make a prototype. And they said they don't know how to make a prototype. I said, well, your PhD students, you should be able to figure it out. So we figured out that a box within a box is the simplest way to go for this. Okay, take the MOF, put it in a small box, then put that box in a larger box, and then this is what the box looks like. It's poly. It's a. Well, I forget now. It's a plexiglass. Excuse me, plexiglass, made of plexiglass, very cheap, and the students went to the desert. This is the amazing thing about students. They are the heroes, right? So with sufficient motivation, they went to the Arizona desert and showed that in fact that device works. It didn't initially. Initially they called me up. No, I called them up at 2 o'clock in the morning and I said, how's the experiment going? And they said, Professor, we see vapor, but it's not condensing. And I said, well, why don't you put part of the box under the ground where it's cooler, slightly cooler, and it should condense. And so, well, they were in an Airbnb, and so they didn't want to dig up the ground. So they went to Home Depot and got sand or whatever and put it around the box, and indeed, it did condense. And later we tested the water, and it's completely pure. It has no metals, no organics, okay? So in fact, it's cleaner than any water you could ever find. It's absolutely pure. The material is very stable in water, so the metals and organics don't leach, as well as the MOF itself, because of the pore size, is a filter, is a molecular filter. He was saying it's nice. But in fact, this is distilled water. So for it to have a nice taste, you need to mineralize it, which is something that could be done easily. Okay, so that was a zirconium MOF. And the nice thing about reticular chemistry is that, if you have a metal like zirconium, which is expensive, it's like $170 or $160 a kilo, you could go to aluminum and make a much cheaper material. And so we made this MOF. I won't describe its structure, but just show you that if you're a molecule floating in the pore of the MOF and you look around the pore, you're going to see a hydrophilic pocket and a hydrophobic pocket. This is exactly the construct on the back of that beetle. There's a hydrophobic, hydrophilic, hydrophobic, hydrophilic, and Avogadro's number of these pockets throughout the material. And so, and the material, as you see here, it takes up water at relative humidity at 5% relative humidity. So in the Atacama Desert, which is the driest desert in the world, this MOF will work. And for the most part, it works at 10% relative humidity. And water can fill the pores and evacuate it from the pores within about 10 minutes. Okay, so here filling up the pores is about 5 to 10 minutes, depending on the humidity. And taking it out of the pores, if you want to enhance the kinetics, you heat it up to 85 degrees, no big deal. And you can get it out within three minutes. So we designed another prototype. This one is more shelf-like to expose the more of the MOF. And in this experiment, they went to the Mojave Desert. And here you see the humidity that they measured during the night and during the day. Okay, it's amazingly different. So during the day, it goes down to almost 10 or 7% relative humidity, but the MOF still delivers water. Okay, so this works. And in this particular experiment, the students use a solar panel to provide power for a fan that pushes air into the MOF. Okay, so that you're not doing one cycle between day and night. So in fact, you push the air into the MOF takes up the water, and then as the MOF gets filled up, you heat up the MOF and then harvest the water. And you can repeat this. And so they delivered 1 liter of water per kilogram of MOF per day. Again, the material is not fully optimized, but still you have 1 liter of water per kilogram of MOF per day at humidities, at really arid region humidities. Okay, so in the first experiment, the Arizona desert, they delivered this much water, actually just a cup of water. And that was completely passive with no energy input aside from ambient sunlight. So you could take that kilogram of MOF, even though it's unoptimized, and let the box sit in the corner, and it will deliver a cup of water every day. Big deal. If you want 100, then you put 100 kilos of MOF, okay? But if you want something that is more productive and could be used in day-to-day, you could use a powered device. And this was the first prototype of a powered device giving you 1 liter. Now we, in collaboration with a startup that I started in the Bay Area, you could have a device no larger than a microwave oven that allows air to go in, and inside this device you have modules of MOF. Some will be exposed to air, while the other ones are the ones already filled up with water can remove the water. And you can see here puddle of water from what is being produced from the MOF. And then the MOF, this is the water that is ultimately collected. So this device uses only 200 grams of MOF. Okay, 200 grams, not kilo, and it produces 5 liters of water per day. Okay, so this is already a device that could be placed in your kitchen and deliver water. So our plans is to not just look at kitchen size, but also a device that sits outside the home to provide enough water, and also what I call village scale devices. The point is that the MOF works, and this device has been working 200 cycles a day for the last 2.5 years, and the MOF still works. So the MOF is graded to stay in the device for about 5 to 6 years. That's 200 grams of MOF. And I know some of you are going to ask me, oh, MOFs are expensive. They're not. Okay, well, if you ask that, I have a very good answer for that. But 200 grams, even if it is expensive, it's still cheap because it's in the device for many years. So it's an aluminum MOF. Aluminum is only $1 or $2 a kilo. And the organic, once it's produced in multi-ton quantities, is quite cheap. So where is the water going into the structure? This is another thing. We're very interested in the basic science of water harvesting so that we can continually improve the performance. And so this is an experiment theory collaboration. And without going through the details, I just want to show you a movie of where each water molecule resides into the structure. And what you'll see one of the pores, and I'm going to slice that in half so that you can see inside the pore, and then you'll see the first water molecules going to the hydrophilic centers, and the hydrophobic centers are not filled with water until the hydrophilic centers are filled, and then more water bridges over the hydrophobic regions, just like in the beetle. So here's the pore. You'll see the hydrophilic regions have the nitrogens in green, hydrogen bond donor and acceptor. This is the first water molecules. There's another position on the blue metal oxide region. Now you see extra water molecules are bridging over the hydrophobic regions here before the structure is completely filled with water. So it turns out that we are able to locate each water molecules incrementally as we fill the pores using single crystal X-ray diffraction. MOF 303 is heaven sent, actually. It's perfect. It has the perfect binding sites. It takes up 45% of its weight in water. It works for many, many years. It has the right binding strength of water so that you don't have to heat up to high temperature to remove the water. But it would be nice, instead of, let's say, if I have a device that delivers 1,000 liters, it would be nice to go to 2,000 liters or 1,500 liters, because that means 1,500, potentially 500 more people could have water, right? So how do I maintain this structure and all the properties, its water harvesting properties, and still expand the pores, right? Because once you expand the pores, then many things could be altered, not the least of which is the way the water is binding into the pore. But we love the way water is binding into the pores. And so our idea was, this is MOF 303 and this is a linker. And so we tried many things, like adding another 5-membered ring to the linker to make it longer. Well, that produces a MOF that is not so stable in water, okay? And then we use 6-membered rings. Then the 6-membered rings are too large. They wedged themselves into the pores and used up the pore volume. And so you didn't get really much for that. In the end, our idea was to add 2 carbon atoms in this way. We call it long arm extension, or LAX series. And this maintains all the binding sites that you want, maintains the hydrophilic pocket and the hydrophobic pocket in the same proximity as before. And it takes up 50% more water. So now 50% more people can have water. Okay, this is MOF 303 on this side. This is the new MOF, LA2, meaning long arm extension with 2 carbons. And you see here that it's taking up 50% more water than MOF 303. And furthermore, the desorption temperature of water is much less. It goes from almost 55, 56, down to 45. So you're even using less energy to take water out of the pores. Okay, so that's how chemistry developed on the atomic molecular level with precision to modify it works for CO2 capture and for water. And if you know the weather conditions all around the year in various parts of the world, then you could say for MOF 303, I can tell you how much that MOF will deliver in water. And you see here different parts of the world, let's say Riyadh or Lanzhou, you see significant amount of water per kilogram of MOF, okay? 40 liters of water per kilogram of MOF per day, based on the device that I just showed you. And you can have fun and do it for many different regions of the world. So finally, I just want to show you that just to be provocative, we wanted to show that in fact the MOF works in Death Valley. Okay, nobody lives there, aside from the park rangers. But here you see that we can design a device that has pancakes of MOF, and it works. Okay, there are bubbles of water. This water is collected from the desert. Okay, by my hero students, okay, who went there and carried out this amazing experiment. So for harvesting water from air, we're making water distributed, mobile, off-grid. You can personalize it to your taste. It's pure for drinking and other things, agriculture if you like. And my dream is to achieve water independence to people everywhere. And I think that this is a perfect example of how You can go from the molecule to the material to engineering that material into a device. And as we speak, these things are being commercialized for society. So I hope at the end of the day that all of us will have water independence. We will have our own devices that are in our control. So since this is an infinite structure space, I just want to say that we teamed up with the computer science department, and we created this Bakar Institute of Digital Materials, which was donated to us by a generous donation by Barbara Baker. And the idea here is to integrate AI and data science and machine learning into speeding up the process of discovering MOFs for different applications. Today I discussed climate or sustainability applications, but this also applies to other applications. So here are my great students that I want to acknowledge above and beyond those that have been already mentioned, our collaborators for financial support, and thank you very much. It's an honor to be here and to receive the Exner medal. Thank you.